Hello everyone, my name is Priya and today I am going to prepare a video recording lecture for visually impaired students on the topic soft and hard acid and bases from Inorganic Chemistry Volume 3 by Dr. K. Bhasin. So let's start now. The terms acid and bases are routinely used in our daily life. Chemists have been classifying substances as acid and bases since long time. Lavoisier noted that the common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius, a Swedish chemist, developed the theory of acid and bases, known today popularly as Arrhenius theory of acid and bases. According to Arrhenius, an acid is a substance which gives hydrogen ion, and that is H positive ion in aqueous solution, and a base is a substance which gives hydroxyl ion OH negative ion in aqueous solution. The strength of an acid or a base depends upon its capacity to provide H positive and OH negative ions respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative is in equilibrium with H2O. In 1923, Jan Bronsted in Denmark and T.M. Lorvie in Great Britain independently proposed a new acid-base theory. According to their theory, an acid is a proton donor whereas a base is a proton acceptor. The acid-base reaction, that is the neutralization, is regarded as a proton transfer reaction. In 1923, Jean Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor while a base is an electron pair donor. The earlier definition of acid and bases were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances that have a sharp or sour taste, turn blue litmus red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substance insoluble in water. On the other hand, the term base was applied to the substances that have a bitter taste, soapy feel, turn red litmus blue. However, tasting and feeling chemicals are dangerous methods of determining whether the substance is an acid or a base. You should never ever taste or touch solution of chemicals in laboratory. There are, however, other methods of recognizing acid and bases. For example, acid and bases change the color of certain dyes known popular as indicators. One of the most common indicators is a vegetable dye obtained from lichen known as litmus. Aqueous solutions of acid turn the litmus red, whereas aqueous solution of bases turn in blue. Thus, any substance which has an unshared pair of electrons can act as a Lewis base, whereas any substance which has an empty orbital to accommodate a pair of electrons act as a Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis bases, and substances capable of accepting a pair of electrons are regarded as Lewis acids. Acid, base, or neutralization reactions may thus be regarded as donor, Lewis base acceptor, Lewis acid reactions, or coordinate covalent bond formation reactions. The classical example of a Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see the boron trifluoride is the Lewis acid and ammonia is a Lewis base. NH3 plus BF3 gives NH3 bond with BF3, donor acceptor or coordinate bond formation reaction. Lewis' concept of acid and bases is very commonly used because of its simplicity and the ease with which the formation of coordination compounds can be explained. In brief, all the usual ligands can be regarded as Lewis bases, whereas all the metal ions can be regarded as Lewis acids. The degree of affinity of a metal ion for ligands can be termed as Lewis acidity, and the tendency of the ligand to combine with the metal ion can be regarded as Lewis basicity. Hard and soft acid and bases. Article 4.1. An acid-base reaction according to Lewis' concept involves the reaction between a donor A and an acceptor B as to form a complex as given below. A plus B gives A bond with B. The formation of the stable complex between the donor A and the acceptor B depend upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive and Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, CO3 positive, Pt4 positive. Based upon the preferential bonding, the acids and bases have been classified into two groups, which class A and class B according to their preference. Class A metal ions include alkali metals, alkaline earth metals, lighter and more highly charged ions, for example, Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive, etc. Hydrogen ion H positive. Class B metal include heavier transition metals of second and third transition series with Cd2 positive, Hg2 positive, Pa2 positive, Pd2 positive, Pt2 positive. Heavier transition metals in lower oxidation state, which is Ag positive, Hg2 positive, Cu positive. Low valent metals ions such as zero valent metals in metal carbonyls. Depending upon the type of metal ions, ligands can be classified as class A and class B depending upon their preference. Class A ligands include molecules or ions with donor atom nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that class A ligands prefer to form strong complex with class A metal. Class B ligands include molecules ions with donor atom P, As, S, Se, I, etc. Class B ligands prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the terms hard and soft acid and bases for class A and class B metal ions and ligands, respectively. Accordingly, class A metal ions are referred to hard acids while class B metal ions are called soft acids. Similarly, class A ligands are named as hard bases whereas class B ligands are termed as soft bases. In summary, according to Pearson, class A acids are hard acids. H positive, Li positive, Na positive, Be2 positive, Mg2 positive, Cr3 positive, Fe3 positive, etc. Class B acids are soft acids. Ag positive, Pd2 positive, Cu positive, Pt2 positive, etc. Class A bases are hard bases. H2O, NH3, F negative, ROH, etc. Class B bases are soft bases. R3P, R3AS, R2S, R2Se, I negative, SCN negative, etc. Article 4.2. Classification of acid and bases as hard and soft. Pearson observed that it is possible to correlate acid-base interactions on the basis of hard and soft acid and bases. He observed that type A metal ions, that is acid, were small, compact and not very polarizable, and these preferred ligands, that is base, that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ion and the ligands they prefer appear to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship and expressed the hard acid prefer hard base and soft acid prefer soft bases. Classification of acids. A general classification of some common hard and soft acid along with some borderline cases is given in table 4.1. That is, hard bases are H positive, Li positive, Na positive, K positive, Be2 positive, Mg2 positive, Ca2 positive, Sr2 positive, Al3 positive, Sc3 negative, Ga3 positive, En3 positive, La3 positive, Cr3 positive, CO3 positive, Fe3 positive, As3 positive, Ce3 positive, Si4 positive, Ti4 positive, Zr4 positive, Th4 positive, Pu4 positive, Bf3, BaCl3, AlCl3, AlH3, AlCH3 whole 3, Cl3 positive, Cl7 positive, I5 positive, I7 positive, RCO positive, CO2, Nc positive, HX, H bonding molecules. And soft acids are Cu2 positive, Ag positive, Au positive, Tl positive, Hg positive, Pt2 positive, Cd2 positive, Pt2 positive, Hg2 positive, Pt4 positive, Ti3 positive, BH3, GaCl3, GaBr3, etc. Borderline acids are Fe2 positive, CO2 positive, Ni2 positive, Cu2 positive, Zn2 positive, Sp3 positive, Bi3 positive, No positive, etc. An inspection of table 4.1 reveals that hard acids usually have the following characteristics. Number 1. Hard acids are cations of smaller size or lighter element. Number 2. Hard acids are cations of higher oxidation states, for example Cl3 positive, Cl7 positive, I5 positive, I7 positive. Number 3. Hard acids are molecules or cations with lesser number of valence electrons. Number 4. Hard acids hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acids bind strongly to a proton. Hard acids are small sized, compact, and are not easily polarized. A close look at table 4.1 also reveals that soft acids possesses the following characteristics. Number 1. Soft acids are cations of larger size or heavier elements. Number 2. Soft acids are cations of lower charge. Number 3. Soft acids are molecules or ions with large number of valence electrons. Number 4. Soft acids do not hold the valence electrons tightly and are therefore easily polarizable. In summary, soft acids are large-sized and easily polarizable ions or molecules that bind strongly to highly polarized ion or molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such type of acids that are neither hard nor soft are called borderline acids, which are shown in the extreme right of table 4.1. Borderline acids have properties which are intermediate between that of a hard acid and a hard base. In case of borderline acids, the properties such size, oxidation state, polarizability of the cation or molecule are neither too low nor too high. On the other hand, soft acids will show the opposite trend and the following order of preference. For binding the donor atoms or ions without a group is I negative greater than Br negative greater than Cl negative greater than F negative, R2Te greater than R2Se greater than R2S greater than R2O, R3Sb greater than R3As greater than R3P greater than R3N. The above trend can also be pictorially represented. Question 4.1. What type of interactions do you expect between a hard acid and a hard base? Answer. Since both hard acids and hard bases are not easily polarizable, their interactions are predominantly ionic. Question 4.2. What type of interactions do you expect between a soft acid and a soft base? Answer. Since both acid Both soft acid and soft base are usually polarizable. The interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly used ligands, that is Lewis bases, into hard and soft bases along with the borderline bases is presented in table 4.2. A glance at the table 4.2 reveals some of the important characteristics of hard bases. Number 1, hard bases bind strongly to the proton. Number 2, hard bases contain donor atoms of high electronegativity. Number 3, donor atoms in hard bases possesses low polarizability. Number 4, hard bases are not easily oxidized. Number 5, hard bases contain empty orbitals of high energy. In summary, hard bases bind strongly to a proton, the donor atom in case of hard bases of an electronegativity and low polarizability. A further inspection of table 4.2 reveals that the following features are observed in case of soft bases. Soft bases contain donor atoms of low electronegativity. Soft bases contain donor atoms of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative non-metal including C, S, P and I. The donor atom in such bases possesses donor atoms that are easily polarized. Just as they are borderline acids, there are borderline bases also. The properties of borderline bases are in between those of the soft and hard bases. It is important to note that the categories are not rightly divided. For example, the halide ions form a series from the very hard fluoride ion, though the borderline chloride ion to the borderline bromide ion and the soft iodide ion. The soft acids, also known as class B metal ions, are the group of metal ions that are in the lower proton of the metallic elements as shown in figure 4. Article 4.3 Pearson's hard and soft acid and base principle. Pearson proposed a simple rule for predicting the stability of coordination compound formed between acid and bases. This rule is quite often named as hard and soft acid and base principle. According to Pearson, hard and soft acid base principle, hard acids prefer to bond with hard bases while soft acids prefer to bond with soft bases. It is important to note that hardness and softness of acids and bases refer only to hard and soft interactions. It is by no means related to the strength of acids and bases. For example, both F negative and OH negative ions are hard bases, but the basic strength of OH negative ion is nearly equal to 10 raised to power 13 times that of F negative ion. Article 4.4 Applications of hard and soft acid and base principle. Pearson's principle of hard and soft acid and base has a number of applications in inorganic chemistry. Some of these are discussed below. Number 1. Stability of the complex. We have already noted that hardness and softness of acid and base are related only to the hard and soft interactions. Hardness and softness of acid and bases have nothing to do with the inherent acidic or basic strength of the acids and base. For example, both OH negative and F negative ions are hard base, although OH negative ion is more stronger as base than F negative ion. In fact, OH negative ion is 10 raised to power 13 times more stronger as a base than F negative ion. However, in hard and soft acid and base principle, both OH negative and F negative ions are at par with each other. Pearson in 1963 explained the relative stability of coordination complexes on the basis of hard and soft acid and base principle. Let us consider a general reaction between a Lewis acid and a Lewis base. A Lewis acid, B Lewis base give A bond with B complex. The complex AB will be most stable if A and B are either both hard or both soft. The complex AB will be least stable if A is hard and B is soft, or A is soft and B is hard. The rule of thumb in determining the stability of the complex is the preferential formation of hard and soft interactions. Exercise: why COF63 negative complex is more stable than COI63 negative. Solution: in both the complexes COF63 negative and COI63 negative, the oxidation state of cobalt is +3. CO3 positive is a hard acid, therefore it combines with a hard base, that is F negative, will lead to COF63 negative, which is a hard interaction. On the other hand, combination of CO3 positive with a soft base I negative will lead to COI63 negative, which is a hard soft interaction. Thus, COF63 negative is more stable than COI63 negative. It has also been noted that the combination of hard or soft ligands with a metal ion is also preferred over a combination of a mixture of hard and soft ligands with a metal ion. For example, the complexes COCN5I3 negative and CONS3 whole 5F whole 2 negative are far more stable, whereas the complexes COCN5F whole 3 negative and CONS3 whole 5I whole 3 positive are unstable. This is because Cn negative and I negative are both soft bases, whereas NS3 and F negative are both hard bases. Number 2. Classification of acids and bases. The acid and base can be classified as hard or soft depending upon their preference for hard and soft reactants. Article 4.5 Limitations of hard and soft acid and base principle. The hardness and softness of a acid or base is primarily related to stability of the hard and soft interactions. It has no concern with the acidity or basicity of the acid or base. For example, OH negative and F negative are well-known hard bases. However, the basicity of hydroxide ion OH negative is very large as compared to the fluoride ion. In fact, the basicity of hydroxide ion is nearly equal to 10 raised to power 13 times than that of fluoride ion. A strong acid is well known to displace a weak acid. Article 4.6 Symbiosis. Jorgensen 1968 observed that the hard ligands have a tendency to combine with a metal ion having hard ligands, and soft ligands have a tendency to combine with a metal ion already having soft ligands. He coined a term symbiosis for these interactions. Electronegativity and hardness and softness. Hardness and softness are related to electronegativity. Species with higher electronegativity values are assigned greater hardness, and those with lower electronegativity values are assigned greater softness. Electronegativity conventionally means the power of an atom in a molecule to attract electrons towards itself. However, in this case, it refers to the power of an individual ion participating in a reaction. For example, lithium ion is known as highly electropositive or lowly electronegative metal, but the cationic species Li positive with very high second ionization potential has a greater tendency to attract electrons towards itself. As a result, Li positive is considered to be more electronegative, and hence it is a hard acid. On the other hand, heavier transition metal ions in low oxidation state like Cu positive, Ag positive, Hg positive, Cd positive, etc. have relatively low second ionization potentials and consequently possesses low value of electronegativity. As a result, these ions are considered as soft acids. Using the same concept of electronegativity, we can define hard and soft bases. The relationship between hardness and electronegativity can explain several important features as below. Trifluoromethyl group CF3 is a harder compared to methyl group. Boron trifluoride is harder compared to borane. Ammonia is harder than trimethylamine. Trifluorophosphine PF3 is harder than phosphine. PS3, which in turn is harder than trimethylphosphine.